AI Neuro-Symbolic AI Deep Dive. How senior engineers master the fusion of neural networks and symbolic reasoning in modern AI systems. Welcome to Agentic AI World. I'm your host, and today we're going deep on one of the most powerful and most underestimated ideas in modern AI, Neuro-Symbolic AI. This is episode 87, and if you're preparing for senior AI engineering interviews, you need to understand this topic cold. Let's get into it. What is Neuro-Symbolic AI? Neuro-Symbolic AI combines two historically separate paradigms in artificial intelligence. First, there's neural learning, deep learning, transformers, embeddings, systems that learn patterns from massive data but struggle to explain their reasoning. Second, there's symbolic AI, logic, rules, knowledge graphs, constraint solvers, systems that reason explicitly but need handcrafted knowledge and can't generalize from raw data. Neuro-Symbolic AI fuses both. The result: systems that can learn from data and reason with structure. They can answer what and why. They generalize better with less data. They're more interpretable, and they fail more gracefully. Here's the analogy interviewers love. A pure neural network is like a student who memorized every exam ever given. Ask a new question in a new format, and they may fail. A pure symbolic system is like a student who only knows the rules of algebra but has never solved a real problem. Neuro-symbolic is the student who learned algebra from examples and understands the rules. They can tackle anything. Why does this matter for senior engineers? Senior engineers ask two questions about any AI system. Does it work, and can we trust it? Pure neural networks score high on the first, but low on the second. Symbolic systems are trustworthy but brittle. In regulated industries, healthcare, finance, law, aviation, you cannot deploy a black box neural system and call it done. You need audit trails. You need the system to say not just, this patient has condition X, but this patient has condition X because their lab results A, B, and C match these clinical criteria. That's symbolic reasoning over neural predictions. In enterprise AI, you often don't have millions of examples. You have domain knowledge, business rules, and a few hundred labeled cases. Neuro-symbolic systems let you inject that structure so the neural components don't have to learn everything from scratch. The core architectures. Let's walk through the main architectural patterns. These are what interviewers will probe. Pattern 1, sequential. Neural first, symbolic second. A neural network extracts features or entities from raw input, text, images, sensor data, and passes structured representations to a symbolic reasoner. Example: a vision model detects objects in a scene. A logic engine reasons about spatial relationships and constraints. This is the simplest integration and the most common in production today. Pattern 2, parallel. Neural and symbolic components run simultaneously and their outputs are combined. The neural component handles uncertainty and ambiguity. The symbolic component enforces hard constraints. You weight their contributions based on confidence. This pattern appears in autonomous driving. Neural handles perception, symbolic handles rule enforcement. Pattern 3, Neural-inside-Symbolic. The neural component fills an uncertainty within a symbolic framework. Think of a knowledge graph where most edges have explicit rules, but some edges, especially for rare or ambiguous entities, are filled by embeddings. Graph neural networks operating over a knowledge base are a good example. Pattern 4, Symbolic-inside-Neural. Rules and constraints are baked into the neural architecture itself. Attention masks that enforce structural constraints. Loss functions that penalize logical violations. This is the most powerful and also the hardest to implement. Researchers call these logically constrained neural networks. Key interview question: how do you handle conflict between neural output and symbolic constraints? This is a classic senior-level question. When a neural network predicts X, but your symbolic rules say X is impossible, what do? There are three approaches. Hard constraint enforcement. Override the neural output whenever it violates a rule. Simple, reliable, but you lose model confidence calibration. Soft constraint penalty. Add a loss term during training that penalizes rule violations. The model learns to avoid conflicts rather than being corrected at inference. More elegant, but requires careful tuning. Probabilistic integration. Treat both the neural output and symbolic constraints as probability distributions and compute the posterior. This is the Bayesian approach and the most principled, but computationally expensive at scale. In production, the answer depends on the stakes. Hard constraints for safety-critical rules. Soft constraints for business logic. Probabilistic for nuanced judgment calls. Real-world applications. Let me give you 5 production use cases that come up in interviews. 1. Drug discovery. Neural networks predict molecular properties from chemical structure. Symbolic reasoners enforce chemical validity rules and known reaction constraints. No amount of data training eliminates basic chemistry. You need symbolic guards. 2. Financial fraud detection. Neural models detect anomaly patterns across millions of transactions. Symbolic rules encode regulatory compliance requirements and known fraud patterns. The symbolic layer makes decisions auditable for regulators. 3. Legal AI. Neural models extract clauses and entities from contracts. Symbolic reasoners check compliance against legal frameworks, jurisdiction rules, mandatory provisions, deadline constraints. Pure LLMs hallucinate legal facts. Symbolic grounding prevents that. 4. Robotic task planning. Neural perception identifies objects and states. Symbolic planners generate valid action sequences using domain axioms. This is why Boston Dynamics robots don't just learn to walk. They have planners that know what physical constraints are unbreakable. 5. Healthcare decision support. Neural models predict diagnoses from clinical notes, labs, imaging. Symbolic systems apply clinical guidelines, treatment protocols, contraindication rules, dosing constraints. Doctors need to explain their decisions to patients. Symbolic reasoning enables that. Scalability challenges. Here's where interviews get technical. The classic knock on symbolic AI is that it doesn't scale. Combinatorial explosion in reasoning, brittle rule sets that can't handle exceptions, expensive knowledge engineering. How do neurosymbolic systems address this? For combinatorial explosion, neural components provide learned heuristics that prune the symbolic search space. Instead of exhaustive logical search, the neural model says, here are the top 10 plausible paths, and the symbolic reasoner checks only those. This is how AlphaGo works conceptually. Monte Carlo tree search guided by neural value and policy networks. For brittle rules, neurosymbolic systems treat rules as soft priors rather than hard axioms. Rules that don't fit the data can be relaxed automatically. The symbolic system learns weights on rules from examples. 4. Knowledge engineering costs. Embedding-based knowledge graph completion replaces manual curation. You write the seed rules. Neural components fill the gaps by learning entity relationships from data. Interview framework. The Neuro-Symbolic Design Matrix. When you get a design question involving Neuro-Symbolic AI, use this 4-axis framework. Axis 1. Separation versus integration. Are the neural and symbolic components loosely coupled, exchanging structured outputs, or tightly integrated, training jointly? Axis 2. Learning versus reasoning. What fraction of intelligence comes from learned patterns versus explicit reasoning? 4. High-stakes domains with clear rules, lean symbolic. For perception and language, lean neural. Axis 3. Hard versus soft constraints. Are rules hard guards or training signals? Map to the constraint handling approach I described earlier. Axis 4. Offline versus online reasoning. Does symbolic reasoning happen at training time, at inference time, or both? Offline constraint learning is cheaper. Online constraint checking is more flexible. Work through these 4 axes for any system design question, and you'll have a structured answer that demonstrates senior-level thinking. What interviewers really want to hear. Senior AI engineering interviews aren't about theory. They want to know, have you shipped something, and do you understand the trade-offs? Neuro-symbolic is a trade-off conversation. You're trading raw neural flexibility for structure, interpretability, and reliability. You're accepting higher implementation complexity in exchange for auditability and data efficiency. The candidates who win senior AI roles are the ones who can say, I know when to reach for a pure neural solution, when to add symbolic grounding, and exactly what changes when I do. That's the answer. Know your tools, know your constraints, know your trade-offs. Quick recap. Neuro-symbolic AI fuses learned representations with explicit reasoning. Key architectures: sequential, parallel, Neural-inside-Symbolic, Symbolic-inside-Neural. Core challenge: handling conflicts between neural output and symbolic constraints. Use hard, soft, or probabilistic approaches depending on stakes. Real-world impact: healthcare, finance, legal, robotics. Design framework: separation versus integration, learning versus reasoning, hard versus soft constraints, offline versus online. That's episode 87. Keep studying, keep shipping, and I'll see you in the next one. This is Agentic AI World.